Welcome to Advanced Foundation Maths lecture series. In this lecture, we will cover chapter 8, which is probability. So let's get into it. Now, even before we start with the formula of probability, let's see few terms that we must know. So first is an experiment. Experiment is any kind of activity such as tossing of a coin, throwing a die, drawing a card, which results in well-defined outcomes. Meaning any activity which is of interest to us, which has well-defined outcomes. Next is random experiment. It is an experiment whose outcomes cannot be predicted and all outcomes are equally likely to occur, meaning an experiment performed randomly. Next is sample space. It is a set of all possible outcomes and is denoted by capital S. Event. An event is an occurrence of something as a result of the experiment. An event is always a subset of the sample space. Now let's see the formula of probability of an event A. It is denoted by P of A and it is equals to number of favorable outcomes divided by total number of outcomes. Total number of outcomes would be the number of element in set S, which is the sample space. So it is denoted by n of S, meaning number of elements in sample space. And in the numerator, we have n of A, meaning number of elements in A, that is, number of cases favorable to event A. So let's take an example of a random experiment. So let's say we toss two coins together. So when we do so, we have something called a sample space. It is set of all possible outcomes. So when two coins are tossed, we have either head-head as an outcome, or head-tail as an outcome, or tail-heads, or tail-tail. So the sample space has these four elements, meaning these four possible outcomes. Now let's define an event A, which is getting at least one tail. So if we want at least one tail in the toss, so it is very clear that we don't want this case where we get both heads. This case would work just fine because it has one tail, and then two tails is also fine because at least means one or more tails. So A would have three elements, HT, TH and TT. So if we need to find the probability of event A, so that would be equals to number of elements in A divided by number of elements in sample space. Number of elements in A is 3 divided by number of elements in sample space is 4. So this is the required probability in fraction form. Now let's see various types of events. So first is simple event. It is an event containing only one element. Next is compound events. It is an event containing two or more elements. Then equally likely events are events whose probability of occurrence are same. Meaning these are events which are equally likely to occur. That is, they have the same probability. Next is mutually exclusive or disjoint events. Two events A and B are said to be mutually exclusive if probability of A and B simultaneously happening is 0. It is denoted by P of A intersection B. Let's see an example to understand these various types of events. So let's say we throw a dice. So a single event can be getting a number 5 because it will have only one element, which is 5. An example of compound event is getting a number 2 or 3. Now this event has two elements, which is 2 and 3. An example of equally likely events is getting a number 2 and getting a number 3 because probability of getting a number 2 is 1 by 6 and probability of getting a number 3 is also 1 by 6, meaning these are equally probable events or equally likely events. Example of mutually exclusive events is getting an even number and getting an odd number. Now if you realize, the intersection of getting an even number and getting an odd number is phi, meaning it is not possible. So therefore, these two events are mutually exclusive because they do not have any intersection. Next is independent events. Two events A and B are said to be independent if occurrence of event A does not affect occurrence or non-occurrence of event B, meaning A and B are independent. Also, students must note here that if A and B are two independent events, then P of A intersection B equals P of A multiplied by P of B, meaning probability of simultaneous occurrence of independent events is equals to multiplication of their individual probabilities. Now let's see a few things that we need to know. If A and B are two events, then A union B means occurrence of at least one of the event A or B. This can also be represented by Venn diagram, where we have drawn two circles. So let's say this circle denote the event A and this circle denotes the event B. So when someone says what is A union B, so A union B is all of these, which is either A occurs or B occurs or both of them will occur. Now next is A intersection B. It stands for simultaneous occurrence of event A and B. So A intersection B is this part where A and B both occur simultaneously. A complement or A bar stands for non-occurrence of A. Similarly, A complement intersection B complement stands for non-occurrence of both A and B. Also, if you recall, we know the De Morgan's law, which states that A complement intersection B complement equals A union B the whole complement, meaning non-occurrence of any of the event A or B. Next is probability of A union B equals probability of A plus probability of B minus probability of A intersection B. Next is probability of A complement equals 1 minus probability of A. Now this is intuitive. Let's say someone tells you that the probability it will rain tomorrow is 60%. So what is the probability it will not rain tomorrow? So the answer is 1 minus 100 minus 60%. So that would be 40%, which in fraction would be 1 minus 0.6. So that will give you 0.4 probability. Next is probability of A union B union C equals probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. All of these is coming from set theory. Now next is probability of A complement union B complement equals probability of A intersection B whole complement. So this is De Morgan's law. Now we know probability of A intersection B whole complement would be equals to 1 minus probability of A intersection B. Similarly, we have this formula. Next is probability of A intersection B complement. So let's see this using Venn diagram. So let's say this circle denotes event A and this denotes event B. So if we want A intersection B complement, so that would be this region. So it is obvious that we subtract the intersection part from A to get P of A intersection B bar, which is this. And similarly, we can understand this formula as well. Now let's do a few questions. 3 identical dice are rolled. Find the probability of getting the same number on each of them. So even before we start the question, let's see the sample space. So if we realize in the sample space, we will have 1, 1 and 1 and then 1, 1, 2, and then so on. So there will be lot of possible outcomes when we throw three identical dice. So we need not actually write down all the possible outcomes. We just need the count of all the possible outcomes. So that is n of s, meaning total number of outcomes. So if you realize, we have 6 outcomes. For the first one we have 6 possibility, for the second one we have 6 possibility, and for the third one we again have 6 possibility. So n of s would be equals to 6 cube, which is 216. Now let's start with the first part. Find the probability of getting the same number on each of them. So let's call this as event A. Now we want the same number on all the 3 dice. So that would be 1, 1, 1, or 2, 2, 2, and so on. The last would be 6, 6, and 6. So the answer would be 6 divided by 216. So that would be equals to 1 by 36. So the probability of getting the same number on each of them is 1 by 36. Now next is getting exactly 1, 3. Now getting exactly 1, 3, let's call this as event B. Now B will contain a lot of elements. We need not write all the elements, we just need to count them. So let's draw 3 boxes which represent the outcomes. So we want exactly 1, 3. So let's say we get 3 on the first dice. For the second dice we don't want 3, so the number of choices is 5, and similarly the number of choices is 5 because we don't want 3 here. So the answer, and for the first one we have just one choice, which is 3. So the answer would be 5 square. Now 3 can be either in the first, now 3 can come on the first die or the second die or the third die. So this multiplied by 3 would be the number of elements in B. So that would be equals to 75. So the answer for the second part would be 75 divided by 216. So this would be our answer. The third is getting at least 1, 3. Now if we want at least 1, 3, so that means we can have either exactly 1, 3 or exactly 2 3s or exactly 3 3s. Probability of at least 1, 3 would be equals to 1 minus probability of getting no 3s. Because this event is complement of at least 1, 3. Now we just need to find the probability of getting no 3s. So let's make 3 boxes which represent the 3 possible outcomes. Now for the first one we have 5 choices because we don't want 3, 5 choices and 5 choices. So the answer would be 5 cube divided by 6 cube. So 1 minus 5 cube, which is 125, divided by 216. So the answer would be 91 divided by 216. So this is the answer for getting at least 1, 3. Now next is getting at most 1, 3. So if we want at most 1, 3, so that is equals to probability of getting no 3 plus probability of getting exactly 1, 3. Now since these are mutually exclusive, we don't need to subtract p of this intersection this, because that would be 0 anyway. So the answer to this would be probability of no 3 is 125 divided by 216 we just saw, plus probability of getting exactly 1, 3, which is 75 divided by 216. So that would be 200 divided by 216. So that would be equals to 25 divided by 27. Now last is, what is the probability of getting the numbers 1, 3 and 5? So we want 1, 3, 5. It may be of this order, or it could be 1, 5, 3, and then 3, 1, 5, then 3, 5, 1, then 5, 1, and then 5, 3, 1. So we can count this, it would be 6. Instead of writing, we could have also counted it by the number of ways we can arrange 1, 3 and 5. So that would be 3 factorial, which is 6 divided by 216. So that would be equals to 1 by 36. So this is the probability of getting 1, 3 and 5. Now one more thing to note here is that probability we got in fifth is same as the probability we got in first. So we can imply that the probability of getting the same number on each of them and the probability of getting the numbers 1, 3 and 5, both these events are equiprobable because they have the same probabilities. So these two are equally likely events. Let's do few more questions. We are given a regular hexagon. Now 3 of the 6 vertices of regular hexagon are chosen at random. The total number of different ways we can select 3 vertices of this hexagon. So the number of elements in the sample space would be the number of ways we can select 3 out of 6 vertices. So that is 6C3, number of ways of selecting 3 vertex out of available 6. Now we need to find the probability that the triangle formed with these vertices is equilateral. Now if you join the vertices, there are only 2 equilateral triangles possible. One is this one, and the other one is this. So n of A is equals to 2 because there are only 2 triangles possible. So probability of getting an equilateral triangle would be equals to 2 divided by 6C3. So there is a bag which contains 2 white balls, 2 black balls and 4 red balls. Now 3 balls are drawn at random. So find the probability that the balls drawn are of different colors. So first let's find the number of elements that would be there in the sample space. So in total we have 9 balls. So out of 9 balls we are selecting 3 at a time. So the number of ways we can do so is 9C3. So these many elements would be there in the sample space. So let's calculate the value. 9 multiplied by 8 multiplied by 7 divided by 3 into 2 into 1. So that would be equals to 84 ways. So there would be 84 elements in the sample space. Now we need to find the probability that the balls drawn are of different color. So n of A, meaning all balls being different color, would be selecting one white, selecting one black and selecting one red. So number of ways we can do so is this. Now which would be equals to 24. So probability of A would be equals to n of A divided by n of S. So that would be equals to 24 divided by 84. So that would be equals to 2 by 7, which is the required probability. Now next question is, let A and B be two independent events such that PA equals 0.3 and PA union B equals 0.8. Then find P of A intersection B. So even before starting with the first part, let's see what independency means. So if A and B are independent events, then P of A intersection B equals P of A multiplied by P of B. Now we do not know the value of PB, so we'll just assume its value. So let P of B equals X. So this would be equals to P of A is 0.3 multiplied by X, or 0.3x. Now we know another formula. P of A union B equals P of A plus P of B minus P of A intersection B. So if this is the case, P of A union B is given as 0.8, P of A is 0.3, P of B is x minus, this would be 0.3x. So this implies 0.8 minus 0.3 equals x minus 0.3x is 0.7x. So x would be equals to 0.8 minus 0.3 is 0.5. So divided by 0.7. So that would be equals to 5 by 7. So probability of B is 5 by 7. So we got the second part of the question. So this is 5 by 7. Now what is probability of A intersection B? So this equals probability of A multiplied by probability of B. Now probability of A is given as 0.3 multiplied by probability of B, which is 5 by 7. So that would be equals to 3 by 10 multiplied by 5 by 7. So 3 divided by 14. Now probability of A complement union B complement is equals to probability of A intersection B the whole complement using De Morgan's law, and this equals 1 minus probability of A intersection B. So that equals 1 minus. Now this value is 3 by 14. So 1 minus 3 by 14. So this would give us 11 by 14. Now probability of A intersection B complement equals probability of A minus probability of A intersection B. Now probability of A is 0.3. Probability of A intersection B is 3 by 14. So this would be 3 by 10 minus 3 by 14. So the answer would be 3 divided by 35. Next question is, there are 3 shooters A, B and C who can successfully hit a target with a probability of 1 by 3, 1 by 4 and 1 by 5 respectively. If all of them fire simultaneously, then find the probability that all of them hit the target. So even before we start, let's define few events. So let event A denotes that shooter A successfully hits the target. Same thing for B and same thing for C. So the probability that all of them hit the target would be equals to P of A intersection B intersection C, meaning A, B and C simultaneously hitting the target. Now since probability of A successfully hitting the target is independent of probability with which B would hit the target, meaning A, B and C are independent, therefore P of A intersection B intersection C would be equals to P of A multiplied by P of B multiplied by P of C. So that would be equals to 1 by 3 multiplied by 1 by 4 multiplied by 1 by 5. So that equals 1 by 60, which is the answer. Now what is the probability that none of them hit the target? Meaning A does not hit the target, intersection B does not hit the target, intersection C does not hit the target. So that would be equals to probability of A complement multiplied by probability of B complement multiplied by probability of C complement. So that would be equals to, what is probability of A not hitting the target? So that is 1 minus 1 by 3, because P of A complement would be equals to 1 minus P of A. Same thing will be used for probability of B complement, that would be 1 minus 1 by 4, and for C complement it would be 1 minus 1 by 5. So that would be 2 by 3 multiplied by 3 by 4 multiplied by 4 by 5. So that would be equals to 2 by 5. Now next is probability of, now next we need to find the probability that target is hit. So that would be equals to probability of at least one of A, B or C hitting the target, which would be equals to 1 minus probability none hits the target. So that would be equals to 1 minus P of A complement intersection B complement intersection C complement. So that is 1 minus This is same as the second part, so 1 minus 2 by 5, so the answer is 3 by 5, which is the required probability. Now next question is, the letters of the word Mississippi are written down at random in a row. Find the probability that no two I occur together. So first let's see the number of elements in the sample space. So we are writing this word by rearranging its letters. So the number of different possible words with or without meaning would be 11 factorial divided by number of times I has been repeated, which is 4 times, further divided by number of times S has been repeated 4 times, and then P has been repeated, so 2 times. So we divide by their factorials. This we have already learned in basic foundation. So this would be equals to 34,650. Now let's find the favorable cases, which is when two I do not occur together. So we will use gap method. This we learned in basic foundation. Now for gap method, we need to first arrange all the letters except I. So that would be M, S, 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 P and P. So the number of ways we can arrange them is 7 factorial divided by 4 factorial because S is repeated 4 times, and then further 2 factorial because P is repeated twice. Now next we count the number of gaps. So in total we have 8 gaps. Now we need to place the 4 I's in any of the 4 gaps. So out of 8 gaps we would select 4 gaps and we would arrange them in the 4 gaps. So that would be 4 factorial, and since all 4 are identical, divide by 4 factorial. So this would be n of A, which would come out to be 7,350. So therefore probability of A would be equals to n of A divided by n of S. So that's 7350 divided by 34650, which upon simplification will give 7 divided by 33. Now next is odds in favor and odds against a particular event. Now these are another way of denoting probability of a particular event. If odds in favor of an event is A is to B, then the probability of occurrence of that event is A by A plus B. If odds against an event is A is to B, then the probability of the occurrence of that event is B by A plus B. Now let's see a question to understand this. In a conference, there are 15 persons seated. Find the odds against two particular persons sitting together. So we need to find odds against an event. So we will first find the probability of occurrence of that event. So probability that two particular persons are sitting together would be equals to n of A divided by n of S. Now n of S is the number of ways 15 persons can be seated around a round table. So if you recall, this is circular arrangement, so our answer would be n minus 1 factorial. So 15 minus 1 factorial, which is 14 factorial. Now we don't need to calculate the value of this, we can just leave it here. Now next is finding number of elements in event A, meaning the favorable number of cases. Now we need to count the number of cases in which the two particular persons are sitting together. So since the two persons must be together all the time, we will consider them as a packet, meaning as one unit. So total count of the elements would be 13 persons plus one packet, so that would be 14. So the answer would be 14 minus 1 factorial, and then these two persons can be arranged in 2 factorial ways internally. So the answer would be 13 factorial multiplied by 2 factorial. So the probability of A would be equals to 13 factorial multiplied by 2 factorial divided by 14 factorial. Now this would be 13 factorial multiplied by 2 factorial divided by 14 into 13 factorial. Now 13 factorial will get cancelled and we will get 2 factorial is 2 divided by 14. So this is 1 by 7. Now this is not the final answer. This is the probability of occurrence of that event. So we will try and write this as 1 by 6 plus 1. So if you compare this with this, we will see that B is 1 and A is 6. So odds against A is to B. Now A is 6 and B is 1. So the answer is 6 is to 1.